Hi, this is Miss Pinkerton. Let's talk about topic 1.5, atomic structure and electron configuration. So let's just review the atomic structure. Remember, in the middle of this Bohr model, and this is a simplified view of an atom that helps us understand. So right here in the middle is the nucleus, and remember the nucleus contains the protons and the neutrons. Then we have these circles, these dashed circles, and these are energy shells or energy levels or even orbitals. But let's just call them energy levels for now, or energy shells. And then the electrons, they reside in these energy levels, and the inner electrons are called our core electrons. And then the outermost electrons are called our valence electrons. And those are what are responsible for chemical bonds and chemical reactions. So we're going to go over how to write the electron configuration and how to draw an orbital diagram really quick. And you'll see over here that there's this method where you can write 1s, 2s, 3s, 4s, all the way down to 7s. And then the next level, you start with 2p, 3p, 4p, 5p. And then the next level, you start with D. And then finally, you go to F. And then you would go like this to write the energy diagram or electron configuration. I'm not good with writing things in this form. I tend to, you have to write them pretty precisely to use this method. And if you want to use that method, that's fine. There's videos that show you how, but I'm going to just show you how to use the periodic table. For me, that actually is easier. And here's an example of an electron configuration for krypton. And it says 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p6. This tells you where each electron is located for krypton in each energy level, where the location is. So I'm going to show you off of the periodic table how to read that. So if I find krypton over here, it's a noble gas, it's 36. This is how I read it. So these tall levels here, which have hydrogen and helium, these are your S levels. Well, and helium over here is S. And you start with 1, 2, 3, 4, 5, 6, 7. Now this next block over here, this lower block, this is your P block, okay? And your P block, we start with 2. So we start and we number it 2, 3, 4, 5, 6, 7. Okay, your P block, all of these, minus helium. And then over here, this is your D block. And your D block, since we started with 1 on our S block and we started with 2 on our P block, what do you think our D block will start with? It starts with 3, and this is 3, 4, 5, 6. Okay? And then finally, you come down here, and this is our F block. And if our P is our F block, and if S started with 1 and P started with 2 and D started with 3, well, our F block starts with 4 and then 5. So if you know that the tall area here is S, and then this section, this second level is P, and this is D, and this is F, and then you just number the S starting with 1, the P starting with 2, the D starting with 3, and the F starting with 4. You can read your electron configuration just by going across the periodic table. So you have to designate where each electron is across the periodic table. So you always start with the first electron, which is 1s in the 1s block, and then you have 2 of them. So we're going to, like I said, we're going to go all the way across here then all the way across here, and then all the way across here, and then finally to here to get to krypton. And we have to show each electron. So what we do is we start with one s, and then we have 2 electrons, 1s2, and then we go down here to 2s, and we have 2 electrons. I'm sorry, I put 2s, a 2. And then we come over here. Well, this is our p block, so we have to go to p, and then I have 1, 2, 3, 4, 5, 6 electrons that are in 2p. Then I come down here and I have 3s, and I have 2 electrons there, and then I have 3. I have to cross my periodic table to 3p, and I have 1, 2, 3, 4, 5, 6, and you'll see you always have 6 in the p's if you go all the way across, and you always have 2 in the s's if you use up all the s's. So I have 4s2. Now I've hit the d block, and that starts with 3, so I have 3d, and if I use up all the d's, you'll count and you'll see that there's 10 squares or electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for the d. And then I've hit my p block again, which is 4p, and I have 1, 2, 3, 4, 5, 6, 4p6. And that's how you write the electron configuration. And you'll notice that it's always the same configuration across the table until you hit your element that you're looking for. So if I wanted to do GE, I would go to 4p2 instead of 4p6, because that's where my last electron is. But everything before that is the same. And that leads us to our noble gas configuration, which we'll practice in a second, because you would literally keep writing the same electron configuration up to the element you're looking for. Okay, so let's practice another one. We have calcium, which is 20. And so if I go to calcium, so I'm going to erase this, erase all these things, all these check marks. And calcium is right here. So again, you're going to see it's the same electron configuration as before. I'm just going to stop earlier because calcium has less electrons than krypton. And so I start with my s block, and I have 2, so 1s2. And then I have my 2s block, so 2s2, 1, 2. And then I hit my p block, which is 2p, and then I have 6. And then I have my 3s block, and I have 2 of those. And then on my 3p block, I have 6. And now I have my 4 block, and I get 2 to calcium, 4s2. So I stop here, and there's 2 in the s block. Now the noble gas configuration is when you find the noble gas that's right before the element you're looking for on the energy level before, and you put brackets around it. So basically you're saying it's the same electron configuration up to argon, and then 4s2. Okay, so that's how you do the noble gas configuration. So I'm going to go ahead and fill that in down here. So I have 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. You kind of start remembering them because it does get very repetitive. Oh no, my periodic table came down to greet me. So 4s2. And then we had AR, 4s2. Now the orbital diagram. Electrons pair up. So in each orbital, you can have 2 electrons, okay? In the s orbitals, there's only one, there's only 2 electrons that can fit. So 2s2. Now the p, remember, the p configuration has 6 electrons, but they still pair up in 2s. So there are actually 3 lines for the 2p orbital diagram. Then we have the 3s, and then the 3p, and then we have the 4s. Now, electrons have what we call a spin, and they have to have opposite spins to fill in an orbital. Not only do they have to have an opposite spin, that they're going to fill in the empty orbitals first before they pair up. So in order to draw the orbital diagram, they're going to pair up on the lowest energy level with opposite spins. So that's why one has these little half arrows. But then when I get to the 2p, the first I'm going to write them all going the same direction in separate orbitals. And then they're going to fill in and pair up. Then the s, they're going to fill in there. And then the p, they're going to fill in separately first with the same spin direction. And then they're going to pair up. And finally s, like that. So why does this matter? So for calcium, it's hard to tell because they're all paired up. But say you had an odd number, 1, and you didn't have the full p filled, it would look something like that. Or say you only have 3 electrons in the p energy level. You would want to make sure they all have the same spin going in separate orbitals first. Okay, so let me redraw that. Or you can just draw the arrows like that too. It doesn't matter. Okay, so that's how you do the electron configuration, the noble gas abbreviation, and the orbital diagrams. Now, Coulomb's law states that like charges repel each other and opposite charges attract. So if you have 2 positive charges, they're going to repel, but if you have a positive and negative charge, they're going to attract each other. And the force of attraction is going to be proportional to the magnitude of the charges and inversely proportional, meaning the reverse, to the square distance between them. And we have Coulomb's law, which explains this force of attraction. And Coulomb's law says that the force is equal to the charge of one particle times the charge of a second particle divided by the radius squared. So one of the trends we have is ionization energy. And ionization energy is the energy needed to remove an electron from an atom. And Coulomb's law explains this trend because if an electron is further away from the nucleus, it requires less energy, right? Because if the R increases, if this increases in the denominator, the F is going to go down, right? And if the electron's closer to the nucleus, it's going to require more energy to remove it. And again, as the radius decreases, the force increases. And we can see this, right? As the radius decreases, this denominator number is smaller, which will create more force, according to Coulomb's law. Now, large jumps in ionization energy indicate that the valence electrons have run out and the electrons being removed is a core electron or an inner shell electron closer to the nucleus. So on the test, or you might get a question and you get a chart like this, it probably wouldn't tell you the element. It would say like X, Y, or Z, and it would ask you how many valence electrons it has. And you'll notice that the chart tells you the first, second, third, and fourth energy to remove those electrons. The first electron, the second electron, the third electron, and the fourth electron. You'll see here that the first electron on sodium is 494 kilojoules per mole to remove. And then there's a 10 times jump. That's huge. And then there's only 2,000 and 3,000. So those are, bigger energies, but this is a 10 times jump. So what this tells you is between this and this, you've hit the core electrons. So there's one valence electron. For magnesium, same thing. You have 736, then it doubles to 1450, then all of a sudden it jumps to 7,000, and then a little 10,000. So again, from here to here, there's a large jump. So that means you've hit core electrons here, and that you have 2 valence electrons that were removed before you hit the core electrons. Here, aluminum, you have 577, 1820, 2,700, and all of a sudden, wow, 11,600. That's a huge jump. So now you've hit the core electrons, which means there's 3 valence electrons here. So it might ask you, like, just from looking at the chart, how many valence electrons are there? Okay, so it's your turn. Can you write the electron configuration for gallium ion Ga3+? Well, before you start this problem, remember Ga3+, does that mean it has more electrons, or did it lose electrons if it has a positive ion charge? Also, please be careful. Valence electrons lose from the higher energy levels first. So higher energy levels before lower energy levels. So good luck with that. Pause and see if you can write the electron configuration for gallium. Let me write my numbers in again. So this is my S block. I've got 1, 2, 3, 4, 5, 6, 7. This is my P block. And I start with 2, 3, 4, 5, 6, 7. And this is my D block, and that starts with 3, 4, 5, 6. And then finally my F block, I'm not going to need that, but 4 and 5. Okay, so I have to go to gallium. Gallium's right here. So I have 1s2, and then I have 2s2, and now I've hit 2p, and I have 1, 2, 3, 4, 5, 6, 2p6. Now I have my 3s block, and I have 2. And then I go over here to my 3p block, and I have 1, 2, 3, 4, 5, 6. 6 of those. Now I have my 4s block, 1, 2. And I have my 4p. Oh, wait, not yet. I skipped my 3d, so I have my 3d block here. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 3d10. And now I have my 4p, and I have 1. So what students will tend to do is they'll just say, I'm just going to go back 3 electrons, 1, 2, 3, and just write the configuration for nickel. And that would be wrong, because what happens is that the valence electrons actually go from the highest energy levels first. So these numbers are the energy levels. So 4 is higher than 3. So you're always going to remove the valence electrons when you're dealing with an ion, a positive ion, or you're always going to remove them from the higher energy levels. So we need to remove 3 electrons. We're going to remove it from 4p1. So that's 1 electron. And then 4s2, because 4s is higher than 3d. It doesn't want to erase. Okay. And then we can move 3d over, and that's the correct electron configuration. So if you write that down here, 1s2, 2s2, 2p6, 3s2, 3p6, and 3d10, that's actually the correct electron configuration when you have an ion. So don't remove them from the D level if you have higher S and P orbital levels.